Welcome to Sleeping Researcher, your peaceful destination for gentle science narration, designed to help you relax and drift softly into sleep. Here, we explore the wonders of the universe with a calm voice and thoughtful pacing, guiding your mind through fascinating topics while soothing your senses. Today, we begin a quiet journey into one of the most intriguing mysteries in science, the reason why the universe seems so remarkably fine-tuned for life. From the precise strength of gravity to the delicate balance of chemical elements, the cosmos appears to be set just right to allow life to emerge and flourish. What does it mean for the universe to be fine-tuned? How do these cosmic conditions come together in such harmony? And what might that tell us about our place in the vast expanse of space and time? In this narration, we will gently explore these questions, inviting you to ponder the subtle intricacies that make life possible. If you enjoy this soothing exploration of science and would like to join us for more peaceful journeys through the mysteries of nature, please like this video and subscribe to Sleeping Researcher. Your support helps us continue creating calming content that nourishes curiosity and relaxation alike. Now, settle in comfortably as we begin our quiet contemplation of the universe's extraordinary balance, where the laws of physics and chance combine to create the cradle of life itself. In the vast expanse of the cosmos, amidst countless stars and galaxies, there exists a profound mystery that has intrigued scientists and philosophers alike for centuries. This mystery revolves around a simple yet extraordinary question. Why does the universe appear so remarkably suited for life? From the tiniest atoms to the grandest cosmic structures, the conditions we observe seem to align with an uncanny precision that allows life, as we know it, to emerge and flourish. This observation sparks a deep curiosity, inviting us to explore the fundamental nature of reality itself. As we embark on this journey, we are drawn into a cosmic puzzle that challenges our understanding of physics, cosmology, and the very essence of existence. At the heart of this puzzle lies the concept often referred to as the fine-tuning of the universe. Simply put, fine-tuning suggests that certain physical constants and laws appear to be set within very narrow ranges, creating an environment where life can develop. For example, slight variations in the strength of gravity, the electromagnetic force, or the properties of subatomic particles would render the universe lifeless and barren. This delicate balance invites us to ponder whether it is a mere coincidence, a result of deeper natural principles, or something even more profound. As we delve deeper, we begin to see that the apparent fine-tuning is not just a curiosity, but a fundamental feature that shapes the cosmic landscape. This realization challenges us to think beyond the surface, to question how and why these parameters are so precisely aligned. Scientists have long sought to understand the origins of this fine-tuning through various frameworks and theories. Some propose that our universe is one among countless others in a vast multiverse, each with different physical constants, and that we happen to exist in the one where conditions support life. Others explore the idea that underlying physical laws or unknown principles govern these constants, ensuring their values fall within life-permitting ranges. The interplay between chance, necessity, and possibility forms a rich tapestry of ideas that continues to evolve with every new discovery. As we reflect on these perspectives, the universe's apparent suitability for life becomes not just a scientific question, but a profound philosophical inquiry. It encourages us to contemplate our place within the cosmos and the deeper meaning behind this cosmic harmony. Ultimately, the question of why the universe seems fine-tuned for life invites us to embrace a sense of wonder and curiosity. It reminds us that our existence is intertwined with the fundamental fabric of reality in ways that are still not fully understood. As we proceed to explore these ideas further, we will encounter fascinating scientific insights and thought-provoking interpretations that illuminate this cosmic puzzle. Each step brings us closer to appreciating the delicate balance that makes life possible and deepens our connection to the universe around us. This journey is one of discovery, inviting calm reflection and open-minded exploration as we seek to unravel the mysteries of the cosmos. When scientists speak of the universe being fine-tuned, they refer to the remarkable precision of certain physical constants and conditions that govern the cosmos. These constants, such as the strength of gravity, the electromagnetic force, or the masses of fundamental particles, appear to lie within an extraordinarily narrow range. If any one of these values were slightly different, the universe as we know it might not have developed the structures necessary for life to emerge. This notion of fine-tuning is not about deliberate design, but rather about the sensitivity of the cosmos to these parameters. Imagine adjusting the dial of a radio just a fraction too far. The signal becomes lost or distorted. Similarly, small shifts in physical constants could prevent stars from forming, disrupt the processes that create chemical elements, or cause the universe to expand too quickly or collapse too soon. This delicate balance creates the conditions where galaxies, planets, and ultimately life can exist. To better understand why fine-tuning is so significant, consider the role of the fundamental forces that shape our universe. Forces like gravity pull matter together, enabling the formation of stars and galaxies, while the electromagnetic force governs the interactions between charged particles, allowing atoms to bond and molecules to form. Even a slight variation in these forces would profoundly alter the cosmos. For example, if gravity were just a bit stronger, stars might burn out too rapidly, leaving little time for planets to develop life. Conversely, if gravity were weaker, matter might never clump together, preventing any complex structures from forming at all. This interplay of forces is finely balanced, creating a cosmic environment where the chemistry of life can unfold. Understanding the subtleties of these forces helps us appreciate why the universe's parameters seem so precisely set, a fact that continues to intrigue physicists and philosophers alike. the concept of fine-tuning extends beyond forces to include quantities like the rate of cosmic expansion and the ratio of different particle masses. Each of these values plays a crucial role in shaping the universe's evolution from the Big Bang to the present day. For instance, the expansion rate must be just right. Too fast, and matter would be too dispersed to form stars. Too slow, and the universe might collapse back on itself prematurely. Similarly, the relative masses of protons and neutrons affect the stability of atoms, influencing the variety of elements available. These precise relationships suggest that the cosmos operates within a narrow window of possibilities that support complexity and life. This delicate tuning prompts us to explore why these parameters fall within such life-friendly ranges, inviting a deeper inquiry into the nature of reality. It is important to recognize that fine-tuning does not imply inevitability or a predetermined outcome. Instead, it highlights the sensitivity of the universe's laws to small changes, revealing a landscape where life as we understand it is possible but not guaranteed. Scientists use sophisticated models and simulations to probe these dependencies, discovering that even minor tweaks to constants lead to vastly different cosmic scenarios. These findings underscore the idea that our existence depends on a precise harmony of conditions. This awareness encourages a sense of humility and wonder as we contemplate the fragile circumstances that make our presence here possible. It also opens the door to questions about the deeper reasons behind this fine-tuning, whether through chance, necessity, or something yet to be understood. As we begin to explore the implications of fine-tuning, it becomes clear that this concept serves as a gateway to profound scientific and philosophical reflection. It invites us to consider not only the properties of the universe, but also the frameworks through which we interpret these observations. Are these finely balanced constants the product of chance among countless possible universes? Or do they hint at underlying principles that guide the cosmos? Each perspective offers a different lens through which to view the mystery, encouraging ongoing curiosity and open-minded exploration. Our next step will delve deeper into these captivating ideas, examining how fine-tuning shapes our understanding of life and existence itself. At the heart of the universe's apparent fine-tuning lie certain fundamental physical constants, values that remain fixed across space and time, shaping the very fabric of reality. Among these, the gravitational constant, often denoted by G, governs the strength of gravity, the force responsible for the attraction between masses. It dictates how stars form, how planets orbit, and ultimately, how galaxies coalesce. Were this constant to vary even slightly, the delicate balance that allows matter to clump and structures to emerge could be disrupted, leading to a cosmos starkly different from our own. Alongside gravity, the cosmological constant plays a subtle yet profound role, representing the energy density of empty space itself. This constant influences the rate at which the universe expands, tuning the cosmic environment in which galaxies and life can evolve. These constants, like silent conductors, orchestrate the symphony of cosmic evolution with remarkable precision. Understanding their values is not merely a matter of measurement, but a doorway into deeper questions about why they hold these particular magnitudes rather than others. The gravitational constant, while familiar in its influence over everyday experiences, such as objects falling to the ground, operates on a scale that extends far beyond. It determines the life cycles of stars, from their fiery births to their eventual fates as white dwarfs, neutron stars, or black holes. A slight increase in this constant could cause stars to burn out rapidly, leaving little time for planets to develop stable, life-supporting conditions. Conversely, a decrease might prevent stars from igniting altogether, resulting in a dark, cold universe, devoid of the energy required to sustain complexity. Similarly, the cosmological constant, often associated with dark energy, subtly accelerates the expansion of the universe. Its value influences whether the cosmos will continue to stretch indefinitely or eventually collapse back on itself. A fine balance here allows for a universe old enough to foster the chemical and biological processes essential to life. These constants are part of a delicate interplay where minute adjustments could yield universes inhospitable to life as we know it. In this light, the precision of these constants invites contemplation about their origin and meaning. But beyond gravity and cosmic expansion, other constants contribute to this intricate cosmic balance. The strength of the electromagnetic force shapes the behavior of atoms and molecules, ensuring the stability of the chemical bonds that underpin biological structures. The masses of fundamental particles, such as protons and electrons, determine the properties of matter itself, influencing everything from the formation of hydrogen atoms to the chemistry of DNA. Each constant exists within a narrow range that permits complexity rather than chaos or void. Scientists continue to explore these values through both observation and theoretical frameworks, seeking to understand whether these constants emerge from deeper physical laws or represent simply one set of many possibilities in a vast multiverse. Such investigations deepen our appreciation of the universe's subtle harmony. This ongoing quest underscores the profound connection between fundamental physics and the emergence of life. The precision embodied in these constants often leads to reflections on the nature of existence itself. Are these values fixed and immutable? Or could they vary in other regions of a larger multiverse, suggesting a cosmic landscape where only certain pockets are hospitable to life? Alternatively, some propose that underlying principles or symmetries yet to be discovered might inevitably determine these constants, weaving a coherent tapestry that necessitates life-friendly conditions. While current science does not provide definitive answers, it offers a framework to examine such questions rigorously and thoughtfully. The recognition of fine-tuning does not diminish the wonder of the cosmos. Rather, it enriches the narrative we tell about origins, structure, and possibility. Each constant thus becomes a portal to deeper inquiry, inviting us to consider not only the universe around us, but the fundamental nature of reality itself. As we continue, we will explore how these constants influence the conditions necessary for life and the broader implications they carry. At the heart of the cosmos lies a remarkable equilibrium, a delicate balance among fundamental forces that shapes the universe as we know it. Gravity, though the weakest of the four fundamental forces, exerts a persistent pull that draws matter together, enabling the formation of stars and galaxies. Yet, gravity alone is not sufficient to craft the intricate structures necessary for life. Electromagnetism, governing the interactions between charged particles, counteracts gravitational collapse in many contexts, providing stability to atoms, molecules, and larger celestial bodies. If gravity were slightly stronger, stars might burn too rapidly or collapse prematurely, leaving little opportunity for complex chemistry or planetary systems to develop. Conversely, if it were weaker, matter would drift apart, preventing the dense clumps needed for star formation. Thus, the precise tuning of these forces ensures that matter can coalesce into stable entities, creating the environments where life's chemical precursors can take hold. Beyond gravity and electromagnetism, the strong and weak nuclear forces play subtle yet crucial roles in the universe's life-friendly character. The strong force binds protons and neutrons within atomic nuclei, allowing the creation of elements heavier than hydrogen. Without this force, operating within a narrow range of strength, these nuclei would either be too unstable to form or too tightly bound to permit the fusion processes that power stars. The weak force facilitates certain types of radioactive decay and nuclear reactions that influence stellar life cycles and elemental abundance. Together, these forces orchestrate a cosmic dance that produces a rich array of chemical elements, forming the building blocks of planets, atmospheres, and ultimately, living organisms. Should any of these forces deviate beyond minuscule margins, the universe's chemical diversity could be drastically diminished, leaving a barren cosmic landscape. This precise interplay highlights an extraordinary harmony, where each force must be calibrated with exquisite care to foster the emergence of complex structures. The formation of stars and planets, fundamental cradles of life, depends on this fine-tuned interaction among forces. Within clouds of interstellar gas and dust, gravity begins its patient work, pulling particles together into denser regions. As these regions grow, pressure and temperature rise until nuclear fusion ignites at the core, birthing a star. The balance between inward gravitational pull and outward radiative pressure from fusion reactions stabilizes the star over billions of years. Around such stars, planets coalesce from remaining material, their orbits shaped by gravitational interactions that maintain long-term stability. This delicate equilibrium enables climates and conditions conducive to life to persist. A slight shift in force strengths could disrupt this process, eliminating stable stars or preventing planets from forming in habitable zones. Thus, the cosmos reveals itself as a finely tuned system, where the forces of nature work in concert to create and sustain environments capable of supporting life. This balance of forces also extends to the properties of fundamental particles themselves. The masses of protons, neutrons, and electrons, along with the strengths of their interactions, influence the way atoms combine to form molecules. The stability of water, the versatility of carbon-based chemistry, and the complexity of organic molecules all hinge on these precise parameters. Slight alterations in particle masses or force strengths could prevent atoms from bonding in ways necessary for the chemistry of life. This interdependence between microphysical constants and cosmic scale phenomena underscores the profound interconnectedness of the universe's design. Every level, from subatomic particles to galactic structures, reflects a finely tuned harmony that allows life not only to exist, but to flourish. These observations continue to inspire inquiry into why the universe exhibits such remarkable precision. At the heart of life as we know it lies carbon, an element uniquely suited to form the complex molecules essential for biology. Unlike other elements, carbon atoms can bond with up to 4 other atoms simultaneously, creating a vast array of stable yet flexible molecular structures. This tetravalency enables the construction of intricate chains and rings that serve as the backbone for proteins, nucleic acids, carbohydrates, and lipids. The versatility of carbon-based chemistry is unparalleled in the periodic table, making it the fundamental building block for the diversity of life. However, this remarkable property of carbon depends on the delicate balance of nuclear forces that govern the behavior of its atomic nucleus. The stability and abundance of carbon in the universe are deeply tied to the fine-tuning of nuclear reactions within stars. In particular, the process of carbon formation, known as the triple alpha process, requires a precise resonance condition between helium nuclei. If the energy levels of carbon-12 nuclei were slightly different, this resonance would not occur efficiently, and carbon would be exceedingly rare. This resonance depends sensitively on the strengths of the strong nuclear force and electromagnetic force, as well as the masses of protons and neutrons. Even minor deviations in these parameters could disrupt carbon synthesis, leaving the cosmos bereft of the element essential for life's chemistry. Thus, the very existence of carbon in sufficient quantities is a manifestation of fine-tuned physical constants. Beyond its formation, carbon's ability to form stable covalent bonds at temperatures and environmental conditions typical of Earth-like planets is also a product of finely balanced forces. The electromagnetic force must be strong enough to hold electrons in tight orbits around the nucleus, but not so strong as to prevent chemical reactions. Simultaneously, the nuclear forces ensure that the carbon nucleus remains stable, preventing it from decaying into other elements. This interplay creates a narrow window where carbon atoms can reliably participate in the complex chemical dance that leads to organic molecules. Without this window, the elaborate molecular machinery required for life's processes, from DNA replication to cellular metabolism, would be impossible. The unique nature of carbon chemistry extends to its ability to bond with other elements essential for life, such as hydrogen, oxygen, and nitrogen. These bonds form the diverse molecules that sustain life's functions, including enzymes and cellular membranes. The precise strengths of these bonds depend on the fundamental constants that set the scale of atomic interactions. If these constants varied even slightly, the chemistry that underpins biological systems would be dramatically altered or rendered non-viable. This sensitivity highlights how the universe's physical parameters are poised to enable the rich complexity of life's molecular architecture. In this way, carbon's central role exemplifies how fine-tuning at the most fundamental level cascades upward to shape the conditions necessary for life itself. As we consider this profound connection between nuclear physics and the chemistry of life, it becomes clear that carbon's unique properties are not a mere coincidence. They arise from a cosmos where forces and constants align with remarkable precision, crafting an environment where complex life can emerge and evolve. This realization invites deeper reflection on the interwoven fabric of physical laws and biological potential. It sets the stage for exploring other facets of fine-tuning that govern the universe's hospitable nature, including the delicate balance of cosmic expansion and the formation of stable planetary systems. Among the many parameters that shape our universe, the cosmological constant occupies a position of profound importance. This constant, often associated with the mysterious dark energy that permeates space, governs the rate at which the cosmos expands. If this value were even slightly different, the consequences for the universe's structure would be dramatic. A larger cosmological constant would cause space to expand so rapidly that matter could never coalesce into galaxies. Conversely, a smaller or negative value might lead to a universe that collapses upon itself before stars and planets have a chance to form. It is within this narrow window of values that galaxies, stars, and ultimately planets emerge, providing the essential habitats for life to take root. This fine balance hints at an underlying harmony between cosmic forces and the conditions necessary for life's existence. The influence of the cosmological constant extends beyond mere cosmic expansion. It shapes the very scaffolding upon which matter assembles. Galaxies, as vast congregations of stars and gas, serve as cradles for the complex chemistry needed for life. Without their formation, the heavy elements forged within stars would remain dispersed, unable to seed planets and organic compounds. The subtle interplay between gravity pulling matter together and dark energy pushing space apart results in a universe that is neither too chaotic nor too inert. This equilibrium allows for the stable environments that life requires, from the nurturing warmth of a star to the protective embrace of a planetary atmosphere. It is a testament to the delicacy of cosmic conditions that life's potential hinges on such an elusive constant. Scientists have long marveled at how the cosmological constant's value appears finely tuned to permit the development of complex structures. If the rate of expansion were altered by even a fraction, the universe's timeline would shift dramatically. Stars might burn out too quickly, or the universe could become a vast, empty void. Such scenarios would preclude the slow, gradual processes of evolution that life depends upon. This sensitivity invites deeper investigation into the origins of dark energy and its role in cosmic history. As researchers probe the nature of this enigmatic force, they uncover more about the fragile conditions that have allowed life to flourish. The cosmological constant thus serves as a window into the intimate relationship between fundamental physics and the emergence of biological complexity. Reflecting on the cosmological constant's role encourages us to appreciate the subtle interconnections that sustain life in the universe. It is not merely the presence of matter or energy, but their precise balance that shapes the cosmic landscape. The interplay of expansion and gravity creates pockets of stability where stars ignite and planets orbit, setting the stage for chemistry and biology to unfold. This remarkable tuning highlights a cosmos that is, in many ways, finely poised for life's arrival, inviting us to explore further the factors that contribute to such a hospitable environment. As we continue this journey, we turn our attention toward the formation of planetary systems, another critical aspect of the universe's life-friendly design. As we ponder the delicate balance of cosmic parameters, it becomes natural to ask why the universe appears so exquisitely suited for life. This question leads us to the anthropic principle, a thoughtful concept that offers insight into our observations. The principle suggests that we observe this universe precisely because its conditions allow observers like us to exist. In other words, the universe must possess certain qualities that make life possible. Otherwise, we would not be here to notice them. This idea is not an assertion of design, but rather a reflection on how the existence of life imposes constraints on the kinds of universes where observers can emerge. It invites us to consider that our vantage point is necessarily conditioned by the requirements for consciousness and complexity. The anthropic principle gently shifts the perspective from wondering why the universe is fine-tuned to recognizing that only in a universe where fine-tuning occurs will beings capable of reflection arise. This subtle yet profound insight encourages a deeper appreciation of our place within the cosmic order, reminding us that our existence is entwined with the fundamental nature of reality itself. To explore this further, imagine a vast ensemble of possible universes, each with different physical constants and laws. In most of these hypothetical realities, the conditions might be inhospitable for the formation of complex structures, let alone life. Stars might fail to ignite, or matter might disperse too quickly for atoms to combine. The anthropic principle proposes that we find ourselves in one of the rare universes where the constants align just right, allowing galaxies, stars, planets, and ultimately life to flourish. This perspective has inspired scientific and philosophical discussions as it frames our universe not as an isolated case, but as part of a broader landscape of possibilities. While the anthropic principle does not provide a mechanistic explanation for why the constants have their particular values, it offers a contextual understanding for why we observe them as they are. It gently reminds us that life's emergence is tied to the very fabric of physical laws, and that our observations are conditioned by the necessity of our own existence. In contemplating why the universe appears finely tuned for life, one compelling idea emerges from the depths of theoretical physics and cosmology: the multiverse hypothesis. This concept proposes that our universe is but one of potentially countless others, each governed by its own set of physical laws and fundamental constants. Within this vast ensemble of universes, the conditions that seem so precisely balanced for life here might be common in some, rare in others, or entirely absent elsewhere. From this vantage point, the apparent fine-tuning is not necessarily a unique cosmic coincidence, but rather a natural selection effect, an observation biased by the fact that we can only exist and observe a universe compatible with life. The multiverse suggests that among a staggering variety of cosmic realms, we find ourselves in one where the constants happen to fall within the narrow window that allows complexity, chemistry, and ultimately life to flourish. This perspective gently reframes the fine-tuning puzzle, inviting us to consider a grander cosmic landscape beyond our observable horizon. Exploring the multiverse hypothesis requires us to extend our imagination beyond the familiar bounds of space and time. Various models of the multiverse arise from different areas of physics, including quantum mechanics, string theory, and inflationary cosmology. For instance, eternal inflation suggests that bubbles of space-time continuously form, each bubble developing its own universe with distinctive properties. In this framework, the physical constants we measure, such as the strength of gravity or the electromagnetic force, could vary from one bubble universe to another. The diversity of these universes implies a cosmic lottery where countless possibilities unfold, but only certain configurations support the emergence of stars, planets, and life. Our presence in this particular universe is thus a consequence of this selection bias. Life can only develop where conditions allow it. This insight offers a subtle yet profound explanation for the fine-tuning, not as a deliberate design, but as a feature of the cosmic ensemble we inhabit. Such ideas encourage a deeper humility about our place in reality, while opening new avenues for scientific inquiry. While the multiverse hypothesis provides an elegant conceptual framework for understanding fine-tuning, it also presents profound challenges for empirical science. By definition, other universes lie beyond our observable reach, making direct detection or measurement exceedingly difficult. Yet, theoretical advances and indirect evidence from cosmology may offer clues. For example, subtle imprints in the cosmic microwave background radiation or patterns in the distribution of galaxies might hint at interactions with other bubble universes. Moreover, the mathematical consistency and explanatory power of multiverse models motivate scientists to explore their implications further. In this way, the multiverse acts as a bridge between philosophy and physics, inviting us to reconsider what constitutes scientific explanation. It reframes the question from, why are the constants finely tuned, to, given many universes, which ones would be observed by conscious beings? This shift in perspective challenges us to embrace complexity and uncertainty in the quest to understand our cosmos. The dialogue between theory and observation continues to unfold, guiding us toward new horizons. While the idea of fine-tuning captivates many by suggesting a universe delicately balanced to support life, it is important to approach such claims with thoughtful skepticism. Critics often point out that the appearance of fine-tuning may be influenced by the limits of our current understanding and the way we frame the questions. For instance, the constants and conditions we observe could be a natural consequence of deeper physical laws yet to be discovered, rather than a rare cosmic coincidence. Sometimes what seems improbable may simply be a reflection of incomplete knowledge, urging us to remain cautious before attributing any special significance to these observations. In this light, fine-tuning may not necessarily imply intentional design or unique rarity, but rather highlight the evolving journey of scientific inquiry into the foundational principles of nature. This perspective encourages us to continually refine our theories and remain open to alternative explanations that do not rely on anthropic reasoning or metaphysical assumptions. Another important critique arises from the anthropic principle itself, which asserts that we observe the universe to be life-friendly because, quite simply, we are here to observe it. This tautological reasoning, while logically sound, does not provide causal explanation. Instead, it draws attention to the selection bias inherent in our observations. Some scholars argue that using the anthropic principle to explain fine-tuning risks shutting down further inquiry by suggesting the question is unanswerable beyond our own existence. Moreover, the principle can be interpreted in various ways, ranging from a weak form stating mere observational facts to a stronger form implying some kind of purposeful tuning. Such ambiguity invites caution and critical examination to avoid overstating the principle's explanatory power. By acknowledging these nuances, we maintain a balanced approach that neither dismisses the mystery nor prematurely claims resolution. This cautious stance fosters a spirit of humility and curiosity within cosmological research. Alternative explanations also emerge from the realm of theoretical physics and cosmology, offering fascinating possibilities beyond traditional fine-tuning arguments. One such approach involves the concept of a self-organizing universe, where certain physical constants and laws arise naturally from underlying symmetries or principles of stability. In this view, the values conducive to life are not arbitrary, but emerge from the dynamics of the cosmos itself. Additionally, some propose that what we perceive as fine-tuning may be an artifact of our limited perspective, shaped by the specific conditions required for observers like us to form. Other hypotheses explore the role of quantum mechanics, information theory, or even unknown dimensions of reality, suggesting that life-supporting parameters could be inevitable or highly probable outcomes. These innovative ideas challenge us to broaden our conceptual horizons and consider that the universe's characteristics might stem from intrinsic patterns rather than chance or design. Such theoretical diversity enriches the dialogue surrounding fine-tuning and invites ongoing exploration. It is also valuable to recognize the philosophical dimensions intertwined with scientific discussions about fine-tuning. Questions about why the universe has the properties it does often lead to reflections on meaning, existence, and the limits of human comprehension. Some thinkers caution against conflating scientific hypotheses with metaphysical or theological interpretations, emphasizing the need to keep empirical investigation and philosophical speculation distinct, yet in respectful conversation. This balance allows science to remain grounded in evidence and testability, while philosophy contemplates broader existential implications. By cultivating this dual approach, we nurture a richer understanding of the fine-tuning issue, one that honors both the rigor of scientific method and the profundity of human wonder. Such interplay between disciplines stimulates deeper inquiry and thoughtful reflection. As we continue to examine the fine-tuning puzzle, the dialogue between proponents and skeptics alike illustrates the essential role of critical thinking in advancing our comprehension of the cosmos. Rather than settling for simple answers, embracing complexity encourages us to question assumptions, explore alternative models, and remain receptive to new evidence. This intellectual openness not only strengthens scientific rigor, but also fosters a sense of humility and awe toward the universe. The ongoing conversation invites us to appreciate the intricate tapestry of factors shaping our existence, while remaining vigilant against premature conclusions. In this way, the discourse on fine-tuning becomes a gateway to ever-expanding horizons of knowledge and wonder. At the heart of modern physics lies the enigmatic realm of quantum mechanics, a domain where the familiar laws of classical science give way to probabilities and uncertainties. This microscopic world, governed by the subtle interplay of particles and waves, may hold clues to the profound question of why the universe appears so finely tuned for life. Quantum effects influence the behavior of fundamental particles, shaping the very fabric of reality on scales far smaller than atoms. It is within this intricate framework that some physicists propose mechanisms capable of subtly adjusting the parameters that govern cosmic evolution. From the strength of fundamental forces to the masses of elementary particles, quantum fluctuations in the early universe could have nudged these values into ranges conducive for complexity and life. Such possibilities invite us to reconsider the apparent precision of cosmic constants, not as fixed, predetermined values, but as outcomes of dynamic quantum processes unfolding over cosmic time. These insights add layers of depth to the fine-tuning discussion, suggesting that the universe's hospitable conditions may emerge from quantum underpinnings that are still being unraveled by science. One of the most intriguing quantum concepts relevant to fine-tuning is the notion of vacuum fluctuations, spontaneous changes in energy that permeate empty space. These fluctuations, fleeting and imperceptible on ordinary scales, could have played a pivotal role during the universe's infancy. In the moments following the Big Bang, quantum effects might have influenced the inflationary expansion, a rapid growth phase that set the stage for the large-scale structure we observe today. The delicate balance of this inflationary process depends on parameters sensitive to quantum fields, suggesting that quantum mechanics did not merely operate in the background, but actively sculpted the cosmic landscape. Moreover, the probabilistic nature of these quantum events introduces an element of randomness that challenges deterministic views of fine-tuning. It may be that among countless quantum possibilities, our universe is one where parameters aligned just right to foster galaxies, stars, and ultimately, life. This perspective enriches the scientific narrative, merging the quantum and cosmological scales in a dance of chance and necessity. Beyond vacuum fluctuations, quantum mechanics also inspires hypotheses such as the multiverse, where our universe is but one of many, each with differing physical constants. In this vast ensemble, quantum phenomena could drive the divergence of universes with varying properties, some inhospitable, others remarkably suited for life. While the multiverse remains speculative, it provides a framework within which fine-tuning may arise naturally, without invoking design or coincidence. Quantum decoherence and the branching of quantum states might be mechanisms through which countless universes emerge, each exploring distinct combinations of cosmic parameters. This quantum branching, if real, redefines fine-tuning as a selection effect, where observers find themselves in those universes compatible with their existence. Such ideas, though challenging to test, encourage us to expand our conceptual horizons and embrace the complexity rooted in quantum theory when contemplating cosmic fine-tuning. The interplay between quantum mechanics and cosmology also highlights the subtle tension between certainty and indeterminacy in our understanding of the universe. While classical physics seeks fixed laws and constants, quantum mechanics reveals a universe imbued with inherent unpredictability. This duality complicates the narrative of fine-tuning, as it suggests that the parameters we observe could be both contingent and emergent, rather than absolute and immutable. Investigations into quantum gravity and the unification of fundamental forces aim to clarify how quantum rules shape the cosmos on the largest scales. These efforts remind us that our grasp of the universe's fine-tuning is provisional, evolving with each advancement in theory and observation. As we delve deeper into the quantum foundations of reality, we open new avenues for understanding the delicate balance that makes life possible. Reflecting on the role of quantum mechanics in cosmic fine-tuning invites a profound appreciation for the complexity woven into the universe's very essence. The subtle quantum processes that operate beyond direct perception may hold the keys to why certain physical constants fall within life-permitting ranges. This perspective encourages an ongoing dialogue between empirical investigation and theoretical innovation, as scientists strive to decode the quantum origins of cosmic order. Embracing the nuances of quantum influence broadens our conceptual framework, revealing that the universe's apparent precision might emerge from a rich tapestry of probabilistic events and fundamental interactions. With each insight, our understanding deepens, guiding us toward the next chapters in the exploration of cosmic fine-tuning. The study of life in extreme conditions, or extremophiles, invites us to broaden our understanding of what it means for the universe to be fine-tuned for life. On Earth, we find organisms thriving in environments once thought inhospitable. Deep-sea hydrothermal vents where crushing pressures and scalding temperatures prevail. Acidic hot springs with pH levels that would dissolve most organic matter. And frozen deserts beneath layers of ice where sunlight barely penetrates. These remarkable adaptations challenge traditional assumptions about the narrowness of life's requirements. If life can persist in such varied and extreme niches, it compels us to reconsider whether the cosmic constants and conditions necessary for life elsewhere must mirror those we observe on our planet. The existence of extremophiles encourages scientific inquiry into alternative biochemistries and diverse habitats, stretching the boundaries of habitability beyond conventional Earth-like scenarios. This opens the door to the possibility that life might arise or endure under different cosmic conditions, perhaps in environments previously deemed too hostile or unlikely. Exploring extremophiles also reveals the resilience and plasticity inherent in life's molecular and cellular machinery. For instance, certain microbes endure intense radiation or complete desiccation by repairing their DNA with extraordinary efficiency, or entering dormant states that preserve vital functions over extended periods. Such capabilities suggest that life's persistence is not solely dependent on finely tuned physical constants, but also on biological ingenuity at microscopic scales. When we consider the universe's vastness and diversity, this adaptability hints that life could emerge in regions with varied temperature ranges, radiation intensities, or chemical compositions, conditions that differ significantly from our familiar terrestrial environment. Consequently, the apparent fine-tuning of universal parameters might encompass a broader spectrum of life-supporting possibilities than previously imagined, challenging us to refine our models and expectations about cosmic habitability. The investigation of extremophiles thus invites a dialogue between astrophysics, biology, and chemistry to unravel the conditions under which life might arise and flourish. In the cosmic context, this interdisciplinary approach encourages the examination of planets, moons, and even interstellar environments that exhibit extreme attributes. For example, the subsurface oceans of icy moons like Europa or Enceladus hold promise as habitats warmed by tidal forces rather than direct sunlight, suggesting that energy sources vital for life can vary widely. These environments differ markedly from Earth's surface conditions, but might still support ecosystems sustained by chemical gradients and mineral interactions. Such insights compel us to question whether the universe's apparent fine-tuning is uniquely Earth-centric, or whether it reflects a broader compatibility with diverse life forms adapted to their specific niches. This expanding vision of life's potential under extreme conditions also reframes the philosophical implications of cosmic fine-tuning. Instead of perceiving fine-tuning as an exclusive design for human-like life, it may represent a universe hospitable to a rich variety of living systems, each shaped by local conditions and evolutionary pathways. The adaptability demonstrated by extremophiles suggests that life's emergence might be a natural outcome of planetary and cosmic processes operating across a range of physical parameters. Such a perspective tempers the notion of a singular set of life-permitting constants, hinting instead at a spectrum where life's defining features arise from interplay between environmental factors and molecular versatility. This evolving understanding encourages us to seek life beyond Earth with open minds, appreciating that the cosmos may harbor forms of existence that challenge our terrestrial intuitions. As we contemplate the lessons of extremophiles and their remarkable tenacity, our journey through the contours of cosmic fine-tuning continues to unfold. By embracing the diversity of life's resilience, we open avenues to explore how the universe might support life in ways not yet imagined. This ongoing quest intertwines with deeper investigations into the fundamental laws and constants, inviting new questions about the relationship between physics, chemistry, and biology on a cosmic scale. With each discovery, we move closer to understanding whether life is a rare cosmic anomaly or a common thread woven through the fabric of the universe, setting the stage for further reflections on the origins and nature of life itself. The vast expanse of the cosmos invites us to consider the delicate balance of its fundamental parameters, a balance that appears essential for the emergence of stars, planets, and ultimately, life itself. To explore this notion, scientists have turned to computer simulations, creating virtual universes where the constants of nature are gently varied. These simulations serve as powerful tools, allowing us to observe how changes in values such as the gravitational constant, the strength of the electromagnetic force, or the masses of elementary particles influence the formation and stability of cosmic structures. By adjusting these parameters within small ranges, researchers can test the sensitivity of the cosmos to such shifts, revealing how even slight deviations may prevent the formation of long-lived stars or the complex chemistry necessary for life. The results often point to a narrow window of conditions where the universe can foster the processes that lead to habitable environments, suggesting a fine-tuning that underpins our existence. One of the remarkable outcomes of these simulations is the insight they provide into star formation, a process fundamental to cosmic evolution. Stars are the forges in which elements heavier than hydrogen and helium are created, elements that eventually become the building blocks of planets and living organisms. When simulations alter the strength of the strong nuclear force or tweak the balance between electromagnetic repulsion and gravitational attraction, the life cycle of stars changes dramatically. Stars may burn too quickly, extinguishing themselves before complex chemistry can develop, or they may fail to ignite altogether. Similarly, the formation of stable planetary systems depends sensitively on the laws governing gravity and motion. These computational experiments reveal the fragile harmony required for stars and planets to persist long enough to host the conditions necessary for life. This delicate interplay showcases the intricate dependencies woven into the fabric of the cosmos. Beyond individual constants, simulations also explore combinations of parameters working in concert, unveiling the multifaceted nature of cosmic fine-tuning. For instance, altering the ratio of the electromagnetic force to gravity can influence the size and lifespan of stars, while changes in the neutron-proton mass difference affect the abundance of elements synthesized in the early universe. These interdependencies highlight how the universe's capacity to nurture life does not rely on isolated factors, but on a complex synergy. Computer models that incorporate multiple varying constants help scientists map out regions of possibility, zones where universes might support chemistry and stable structures, even if they differ from our own. Such explorations broaden our understanding of what fine-tuned might mean, suggesting that while our universe appears exquisitely balanced, there could be other viable configurations. This ongoing research invites us to consider the diversity of cosmic possibilities and the subtle conditions that make life feasible. These computational approaches also offer a glimpse into the profound questions about the origins and nature of the laws themselves. By simulating universes with alternate physical laws or constants, scientists probe the boundaries of what is possible, examining whether life requires the precise conditions we observe, or if alternate pathways might exist. This line of inquiry intersects with philosophical and theoretical considerations, such as the multiverse hypothesis, which posits a vast ensemble of universes, each governed by different parameters. Within this broader context, our universe's fine-tuning might be seen as a natural selection among countless variations, where only certain configurations allow complexity and life to flourish. Computer simulations thus become a bridge between empirical science and deeper metaphysical reflections, enabling us to explore the interplay between chance, necessity, and the profound order underlying reality. These insights deepen our appreciation for the cosmic environment that nurtures life and inspire further exploration into the mysteries of existence. When we contemplate the fine-tuning of the universe, we are drawn to the remarkable precision with which fundamental constants and physical laws align to create a cosmos hospitable to life. From the strength of gravity to the balance of electromagnetic forces, these parameters seem exquisitely set to allow the formation of stars, planets, and complex chemistry. This delicate balance is not merely an abstract curiosity. It directly influences the emergence and sustainability of life as we understand it. In astrobiology, the study of life beyond Earth, this fine-tuning provides a crucial context. The specific conditions that enable stable, long-lived stars and the synthesis of essential elements form the foundation upon which planets with the potential for life can exist. Thus, the search for extraterrestrial life is deeply intertwined with understanding how the universe's underlying design facilitates biological complexity. As we scan the cosmos for signs of life, we are, in essence, exploring the manifestations of this fine-tuning across vast distances and epochs. In examining the cosmic conditions favorable to life, astrobiologists consider a variety of factors that stem from the universe's fine-tuned nature. The presence of stable stars that burn steadily for billions of years provides a consistent energy source, allowing planetary environments to evolve gradually. The abundance and distribution of elements like carbon, hydrogen, oxygen, and nitrogen forged in the hearts of stars are fundamental to the chemistry of life. Furthermore, the laws of physics governing molecular interactions enable the formation of complex organic molecules, which serve as the building blocks for cells and organisms. These interrelated cosmic elements underscore that life is not an accidental byproduct, but a phenomenon emerging within a finely balanced framework. By understanding these cosmic prerequisites, scientists refine their criteria for habitable zones and the types of planets most likely to host life, guiding observational strategies and mission designs. The concept of fine-tuning also influences our interpretation of the rarity or ubiquity of life in the universe. If the parameters of the cosmos were only slightly different, the processes leading to star formation or chemical complexity might fail, rendering the universe sterile. This sensitivity suggests that life might be a delicate blossom in an otherwise inhospitable expanse. Yet the vastness of space and the countless stars and planets within it raise the possibility that even rare conditions could occur frequently somewhere. This tension between fine-tuning and cosmic abundance shapes the scientific quest to detect biosignatures or technosignatures beyond Earth. Each discovery or absence thereof incrementally informs our understanding of how common or exceptional life is, influenced by the subtle interplay of cosmic constants and natural laws. The search for extraterrestrial life thus becomes a profound exploration not only of distant worlds, but also of the fundamental nature of the universe itself. By investigating where life can exist, we gain insight into the parameters that define our cosmic habitat. This endeavor connects disciplines from physics and chemistry to planetary science and biology, all converging on the question of how the universe's fine-tuned properties shape the possibilities for life elsewhere. As our instruments and methods evolve, we move closer to discerning the fingerprints of life across the cosmic ocean, guided by the understanding that the universe's precise tuning is a vital context for this search. Each new observation enriches the narrative of life's potential, deepening our connection to the cosmos and the delicate conditions that sustain us. The universe's fine-tuning presents a profound philosophical puzzle that has intrigued thinkers throughout history. When we observe the delicate balance of physical constants and cosmic conditions that allow life to exist, it invites us to question the nature of reality itself. Why do these parameters fall within such a narrow range, seemingly optimized for complexity and consciousness? This observation challenges the assumption that the cosmos is a random, indifferent expanse. Instead, it suggests a deeper order or purpose that merits careful reflection. The realization that slight alterations in fundamental forces could render the universe lifeless brings into focus the fragile nature of our existence, encouraging a sense of wonder about how and why these precise conditions have come to be. The philosophical implications are vast, touching on concepts of meaning, causality, and the very essence of being. Considering the fine-tuning from a philosophical standpoint also compels us to examine our place within the cosmos. If the universe is configured in such a way that life is possible, then the emergence of conscious beings capable of pondering this fact gains new significance. We might ask whether this apparent suitability for life is a mere coincidence or points toward an underlying principle that connects existence with purpose. Some interpretations suggest that fine-tuning hints at the universe being a kind of cosmic habitat, intentionally or inherently conducive to life and awareness. This perspective invites us to explore the relationship between physical laws and metaphysical questions, bridging the gap between scientific observation and existential inquiry. It is here that science and philosophy find a rare meeting ground, where empirical evidence stirs the deepest human questions about meaning and destiny. Perhaps this dialogue between disciplines enriches our understanding of both the cosmos and ourselves. The enigma of fine-tuning also opens the door to a diversity of philosophical interpretations, each offering a unique lens through which to view our universe. Some propose the anthropic principle, which suggests that we observe these finely tuned conditions simply because only in such a universe could observers like us exist. This viewpoint emphasizes the contingent nature of our existence, without necessarily implying purpose or design. Others consider the possibility of a multiverse, where countless universes with varying physical parameters exist, and we happen to inhabit one that supports life. Both ideas challenge our traditional notions of uniqueness and universality, prompting us to rethink how we interpret chance and necessity on a cosmic scale. These reflections deepen our appreciation of the complexity and mystery inherent in the cosmos, encouraging humility and open-mindedness as we continue to seek understanding. In contemplating these ideas, we engage in a timeless conversation about existence that transcends the boundaries of science alone. The concept of fine-tuning, while deeply rooted in scientific inquiry, has also captured the imagination of popular culture in profound ways. From the pages of science fiction novels to the scenes of cinematic universes, the idea that the cosmos is exquisitely balanced to support life has become a source of wonder and speculation. Creators and storytellers often explore worlds where slight variations in fundamental constants lead to radically different realities, sometimes barren and inhospitable, at other times teeming with unimaginable life forms. This imaginative engagement invites audiences to reflect on the delicate parameters that sustain our own existence, making abstract scientific principles more tangible and emotionally resonant. Through these narratives, fine-tuning transcends sterile numbers and equations, becoming a narrative thread that connects us to the broader mystery of why the universe is as it is. Such portrayals encourage curiosity and inspire a sense of connection between the scientific exploration of cosmic conditions
and the human desire for meaning and belonging.
In scientific circles, the study of fine-tuning extends beyond philosophical speculation into rigorous examination of the physical constants and laws that govern our reality. Parameters such as the strength of the electromagnetic force, the mass of elementary particles, and the rate of cosmic expansion appear to fall within extraordinarily narrow ranges that permit the formation of atoms, stars, and ultimately, life-bearing planets. Researchers investigate how even minuscule deviations in these quantities could preclude the emergence of complexity, highlighting the fragile balance woven into the fabric of the cosmos. This precision raises profound questions about the underlying reasons for such calibration, prompting theories that range from the existence of multiple universes to subtle designs embedded in nature's laws. The fine-tuning debate thus serves as a bridge between empirical observation and deeper existential inquiry, inviting scientists to consider not only how the universe operates, but also why it permits the rich diversity of life we observe. By engaging with this topic, science both acknowledges its limits and expands its horizons in the quest to understand our cosmic environment. The interplay between fine-tuning and human imagination is also evident in the ways these ideas enrich public discourse and cultural identity. As people grapple with the vastness of the cosmos and their place within it, the notion that the universe is finely tuned offers a profound source of comfort and inspiration. It connects the empirical with the existential, allowing individuals to see themselves as part of a grand, interconnected whole. Educational programs, documentaries, and popular science books often highlight fine-tuning as a gateway to exploring the wonders of physics and cosmology, making complex topics accessible and engaging. This shared curiosity fosters a collective appreciation for the delicate conditions that make life possible, nurturing a sense of stewardship and reverence for our world. In this way, fine-tuning becomes not only a scientific concept, but also a cultural symbol that resonates deeply across diverse communities and perspectives. Moreover, the fascination with fine-tuning has sparked dialogue between science and philosophy, encouraging a multidisciplinary approach to understanding existence. Philosophers ponder the implications of a universe so precisely calibrated, questioning whether this points to underlying purpose, random chance, or something yet beyond human comprehension. Scientists, in turn, remain open to these reflections while grounding their inquiries in testable hypotheses and observable phenomena. This synergy enriches both fields, fostering humility and wonder as we confront the profound mysteries of our origins and destiny. The narrative of fine-tuning thus becomes a shared space where empirical knowledge and contemplative thought meet, inviting ongoing exploration and discovery. It is within this dynamic interplay that the story of our universe continues to unfold, inspiring both scientific progress and philosophical insight. In the quest to understand why the universe appears so finely tuned for life, scientists continue to push the boundaries of knowledge through innovative research and experimentation. Advances in cosmology, particle physics, and astronomy offer increasingly precise measurements of fundamental constants and cosmic parameters, allowing us to test the limits of fine-tuning claims. Experiments at large particle accelerators probe the properties of subatomic particles and forces that govern the universe's behavior, seeking deeper insights into the natural laws that shape reality. Observations of distant galaxies and cosmic background radiation provide snapshots of the universe's earliest moments, helping to refine models of cosmic inflation and structure formation. Each new discovery challenges or reinforces our understanding of the delicate balance that enables stars, planets, and ultimately life itself to exist. As technology evolves, so too does our capacity to explore the universe at scales both unimaginably vast and infinitesimally small, revealing layers of complexity that inspire both awe and curiosity. One promising avenue of research examines the possibility of multiple universes, often referred to as the multiverse. This concept suggests that our universe may be just one of countless others, each with its own distinct set of physical laws and constants. If true, the apparent fine-tuning of our universe might be understood as a natural consequence of selection bias. We find ourselves in a universe compatible with life, simply because only such universes can host observers. While the multiverse remains a theoretical framework, ongoing studies in string theory, quantum mechanics, and cosmology strive to find ways to test or constrain its predictions. These efforts underscore the interplay between theory and observation, highlighting the profound challenges of investigating phenomena that may lie beyond direct empirical reach. The pursuit of evidence for or against the multiverse paradigm continues to inspire novel hypotheses and experimental designs, reflecting the enduring human drive to comprehend the cosmos in its entirety. Simultaneously, researchers explore the fundamental nature of the constants themselves, questioning whether what we perceive as fixed values might actually vary across space or time. Precision measurements of fine structure constants, gravitational strength, and other parameters are conducted using distant astrophysical sources and laboratory experiments. Detecting any variation could revolutionize our understanding of physics and potentially offer alternative explanations for the conditions that enable life. Moreover, the investigation into the origins of these constants touches on deep questions about the initial conditions of the universe and the underlying principles that govern its evolution. Such inquiries invite collaboration across disciplines, merging theoretical physics, observational astronomy, and even philosophy, as we seek to unravel the intricate tapestry that defines our cosmic environment. This ongoing research continually expands the horizon of what we know and what remains to be discovered about the universe's fine balance. Beyond the quest to explain fine-tuning, emerging technologies in observational astronomy promise to shed new light on the universe's earliest epochs and on the formation of cosmic structures conducive to life. Next-generation telescopes and detectors will peer deeper into space and time, capturing signals from the first stars, galaxies, and perhaps even hints of primordial phenomena. These observations may reveal subtle patterns or anomalies that challenge current models, or suggest new principles at work. Additionally, advances in computational modeling enable scientists to simulate universes under varying conditions, testing how changes in fundamental constants might influence the emergence of complexity and life. Such simulations offer a virtual laboratory for exploring possibilities that are otherwise inaccessible, helping to contextualize the fine-tuning puzzle within a broader cosmic landscape. As these tools and methods mature, they promise to refine our understanding of the delicate interplay between chance, necessity, and the profound conditions that make life possible. The question of why the universe appears finely tuned for life touches upon some of the most profound mysteries in science and philosophy. At its core, fine-tuning refers to the observation that certain fundamental physical constants and conditions fall within very narrow ranges, allowing for the existence of stable atoms, complex chemistry, and ultimately, living organisms. Slight variations in these constants could render the cosmos inhospitable, preventing stars from forming or atoms from binding together. This delicate balance prompts us to consider whether it is a mere coincidence, a consequence of deeper physical laws, or evidence of a broader multiverse where many universes exist with varying parameters. Each of these perspectives carries profound implications for how we understand our place in the cosmos and the nature of reality itself. The persistent enigma of fine-tuning continues to inspire new lines of inquiry and debate as scientists strive to unravel the subtle interplay between chance and necessity that underpins our universe. One compelling aspect of the fine-tuning discussion lies in the remarkable precision with which the forces of nature operate. For example, the strength of the electromagnetic force, the ratio of the masses of elementary particles, and the cosmological constant all appear calibrated to support the formation of galaxies, stars, and planets. The resonance of carbon nuclei, which enables the synthesis of essential elements in stars, exemplifies this precision. Such exact conditions suggest that the universe's laws are not arbitrary, but exhibit a kind of harmony that fosters complexity. While some propose this fine-tuning arises from undiscovered principles or symmetries in physics, others consider the possibility that our universe is one among many, and we simply find ourselves in one where the parameters align to permit life. These ideas challenge our conventional understanding and open pathways to new theoretical frameworks that seek to explain why the universe permits observers at all. The pursuit to comprehend fine-tuning thus bridges the empirical rigor of physics with the philosophical dimensions of existence. The significance of fine-tuning extends beyond the realm of physics into broader questions about the origin and nature of life itself. Life, as we know it, depends on a complex chain of cosmic events, from the formation of stable atoms to the emergence of planetary environments capable of sustaining biological processes. The fact that these prerequisites are met with such exactness invites reflection on the conditions necessary for life to arise and flourish. It also motivates interdisciplinary research spanning cosmology, chemistry, biology, and even information theory, as scientists seek to understand how complexity emerges from simplicity. This interconnectedness highlights how fine-tuning is not simply a curiosity of numbers, but a focal point for exploring the deep relationship between the cosmos and the living systems it hosts. As investigations continue, the fine-tuning conundrum remains a beacon guiding scientific imagination toward greater insights about the universe and ourselves. Moreover, the mystery of fine-tuning encourages humility in our approach to understanding the cosmos. Despite remarkable advances in observational techniques and theoretical physics, many questions remain unresolved, reminding us of the vastness and intricacy of the universe. The apparent fine-tuning serves as a gentle invitation to remain open to new ideas and discoveries that might reshape our comprehension of reality. Whether future findings reveal hidden symmetries, new dimensions, or an expansive multiverse, the pursuit itself enriches our appreciation of the delicate conditions that make life possible. This ongoing journey exemplifies the spirit of scientific inquiry, patient, thoughtful, and ever curious, enabling us to glimpse the profound interconnectedness of all things. As we continue to explore, the fine-tuning puzzle remains a luminous thread woven through the fabric of cosmic exploration. As we ponder the subtle balance that allows stars to shine, planets to form, and life to emerge, we find ourselves standing at the threshold of deeper cosmic questions. The universe's apparent fine-tuning invites us to continue seeking explanations beyond what we currently understand. Each discovery, whether in particle physics, astronomy, or biology, serves as a stepping stone toward unveiling the mechanisms behind this delicate harmony. It is a gentle reminder that the cosmos is not a static backdrop, but a dynamic, evolving system filled with surprises waiting to be uncovered. This sense of wonder encourages us to maintain an open mind, knowing that new insights may come from unexpected directions, challenging preconceived notions and expanding the horizons of possibility. As scientists refine their instruments and theories, the quest to comprehend the universe's life-friendly conditions remains a beacon, guiding our curiosity forward. The journey toward understanding fine-tuning is far from linear. It is marked by moments of revelation and mystery alike. The notion that fundamental constants and cosmic parameters fall within narrow ranges suitable for life sparks questions about the nature of these values. Are they mere coincidences, products of chance in a vast multiverse, or indications of deeper principles yet to be revealed? Such inquiries do not demand immediate answers, but rather invite continued reflection and exploration. As novel technologies enhance our ability to observe distant galaxies, probe the quantum realm, and decode the origins of life's molecular machinery, each advancement opens new windows into the cosmic narrative. In this ongoing dialogue between observation and theory, the fine-tuning enigma remains a compelling motif that fuels scientific perseverance and imagination. Beyond the scientific dimensions, the fine-tuning puzzle resonates with a broader human desire to find meaning and connection within the vastness of space and time. It encourages a perspective that embraces humility and awe, recognizing that our presence in the universe is intertwined with conditions shaped over billions of years. This awareness fosters a sense of stewardship, urging us to cherish the fragile environment that sustains life on our planet. At the same time, it propels us to look outward, to explore the cosmos not only with instruments, but with a spirit of inquiry that honors the unknown. This interplay between knowledge and mystery enriches our understanding of existence and motivates future generations to continue the quest. Thus, the fine-tuning phenomenon serves as both a scientific challenge and an invitation to remain deeply engaged with the unfolding story of the universe. As we stand poised on the brink of new discoveries, it is essential to remember that the search for answers about fine-tuning reflects the very essence of scientific exploration. A patient, thoughtful journey propelled by curiosity and wonder. Each question answered often reveals further complexities, underscoring the intricate tapestry of physical laws and cosmic events that create the conditions for life. This ongoing endeavor invites us to embrace uncertainty, while nurturing hope for greater clarity in the future. Whether breakthroughs emerge from theoretical insights, experimental data, or serendipitous observations, the process itself enriches our collective understanding and deepens our appreciation for the universe's subtle artistry. In this way, the mystery of fine-tuning continues to inspire us to look beyond the horizon, eager for the next chapter in the story of existence. As we contemplate the delicate balance of forces and constants that shape our cosmos, it becomes clear that this fine-tuning is not merely a scientific curiosity, but a profound invitation to reflect on our own existence. The precise values that govern everything from the strength of gravity to the properties of subatomic particles create a universe where stars can form, planets can sustain atmospheres, and life can emerge. This intricate harmony suggests a cosmos that, while vast and often indifferent in scale, has parameters finely aligned to nurture complexity and consciousness. Such alignment may inspire a sense of awe and humility, reminding us that we are part of a larger story, one written in the language of physics and expressed through cosmic evolution. In recognizing this, we find a quiet celebration of life's resilience and the remarkable conditions that allow us to wonder about ourselves and the universe beyond. The phenomenon of fine-tuning also encourages us to embrace the mysteries that lie at the heart of scientific inquiry. While some may see the universe's life-friendly features as evidence of design or purpose, science invites us to consider all possibilities with openness and rigor. Concepts such as the multiverse hypothesis or anthropic principles offer frameworks where fine-tuning emerges naturally from statistical or environmental selection effects. Yet, the true nature of these explanations remains elusive, encouraging continued exploration rather than definitive closure. This space of uncertainty is where science thrives, where each new theory or observation adds depth to our understanding, while preserving the wonder that fuels our quest. In this way, the universe's fine-tuning becomes more than a puzzle to solve. It becomes a catalyst for imagination and discovery, urging us onward in our search for meaning. Beyond theoretical considerations, the awareness of fine-tuning fosters a deep connection between humanity and the cosmos. We are not isolated observers, but participants in a grand, unfolding narrative that spans billions of years and countless light years of space. Our very atoms were forged in the hearts of ancient stars, linking us intimately to the vastness around us. This cosmic heritage invites a sense of belonging and responsibility, to cherish the fragile conditions that sustain life and to seek harmony within the natural world. As we gaze upward, we may feel a quiet kinship with the universe itself, a recognition that our lives are threads woven into the fabric of cosmic time. Such reflections offer solace and inspiration, affirming that in the vastness of space and time, we are both infinitesimal and profoundly significant. Ultimately, the fine-tuned nature of the universe serves as a reminder of the delicate interplay between chance and necessity, between order and chaos that shapes all existence. It invites us to approach life with reverence and curiosity, acknowledging the extraordinary conditions that make our presence possible. Whether viewed through the lens of science, philosophy, or personal reflection, this cosmic balance encourages a deep appreciation for the mystery and beauty that surround us. Each moment of insight, each glimpse into the workings of the cosmos, enriches our understanding and deepens our gratitude for the gift of being. In embracing this perspective, we find a quiet peace, a recognition that, in the finely tuned dance of the universe, we are both observers and participants, forever connected to the stars from which we came.